Our next presenter, Lorenz Meyer, is going to take this application a step further. Lorenz is a physicist. He was at the 2010, I might get the story a little off, but he was at the 2010 ISSW in Tahoe, and I believe was giving a paper on radar. Somebody asked a question, well, what about it going operational? And that triggered an idea. So he bailed on his job at the SLF, started Geopraevent, his company, and now has an operational radar system that he's going to discuss. Lorenz? And I like to think that's a perfect application of research and practice.
Thank you. So I'm going to talk about an operational system that we are running in Zermatt, and that closes the road with radar in real time. But let me first show you a few fundamental things about radar. And also maybe the talk I had during 2010, that was my last ISSW that you mentioned, where I got the question when those systems would be operational. So I didn't attend any ISSW anymore since then because I was busy setting up Geopraevent. Now I have time. So just shortly to tell you what we do, we install and we develop, install and operate electronic detection systems for natural hazards, meaning we place sensors somewhere up in the mountain. Sometimes it's radar, sometimes it's other sensors. We have usually some alarming system, and we control all those systems remotely from our servers to be sure they're working all the time. We are doing that with a number of natural hazards. I'm talking about avalanches, snow avalanches here. You heard Stefan Marget's talk maybe on Tuesday about glaciers, so that's the location actually he mentioned. We are looking at the reflows, at water, and we also detect people. I'll come back to that shortly. Why do we use radar? There has been presentations about thermal cams on Tuesday. The big advantage of radar is that you can see through fog, through snowfall, and through rain. With a normal camera, you can have a good overview on your terrain and on a sunny day, but already at night, you don't see a lot anymore. With a thermal cam, or also with a laser, it's an active system. You can monitor your area at night as well, but the performance in bad weather situations is very limited. With the radar, you can penetrate fog and that bad weather. And since the systems that need to close a road in real time, they have to work at any weather conditions, because right at bad weather, that's when they are needed most. So the advantages of radar, besides the good weather capabilities, are that you see a large area. You can monitor several square kilometers with the radar. Ranges are up to a few kilometers, and you don't have to go to the area that is endangered. So you don't have to go into avalanche terrain to mount some sensors. So it's also less prone to damage. It's less dangerous to install something. We are using two different radar principles for our project. Just briefly show you this one as well. Interferometric radar is one that we mentioned in a few talks as well. We are looking at slow movements with interferometric radars, millimeters per minute or even per year. So that's movements of rock instabilities of glaciers. This is a glacier that we monitor since 2 years continuously. Every hour we get this kind of plot, and we see if some parts of the glacier accelerates, and usually a few days later they fall off. That's what Stefan Marget told on Tuesday. For the systems I'm going to talk about now, we use Doppler radar. So with Doppler radar we measure fast speeds, we measure rocks falling down, or we measure avalanches. So these are used for alarm systems. We call systems an alarm system if the system itself takes action, meaning closes a road without the intervention of an expert. How does Doppler radar work? Jan Thomas showed that very nicely on Tuesday, and just briefly go back to that. We send radar radiation on a target. If this target is not moving, the radiation is reflected and the frequency is unchanged. However, if the target is moving, the frequency changes and we can see a moving object by that. And as I mentioned, this works as well when there is fog or rain or snow falling between your radar and the person. Now, how does the radar see an avalanche? You remember that from Walter's talk? I just show you briefly what happens here. This is the digital terrain model. This is the Weiss-Mies 4,000 meter high peak. And our radar sees a 90-degree opening angle, so horizontally we see a lot. Vertically we see about 10 degrees, so we see every movement here in this area between 1,500 and 2,000 meters. And as soon as something moves, we can visualize this movement here, what kind of an activity that the radar notices. And as soon as the movement is below the radar antenna, so at the end of the avalanche is now below the radar, so we don't see it anymore. So we have to make sure we cover the area with the radar that we want to monitor. The radar can also see people. This is from an operational project in Zermatt, where they're doing avalanche control, and they want to make sure that nobody has entered the area prior that they do their work, so they don't bury anybody with the avalanche that they are going to trigger. We have up to now installed about 15 radars. By the end of the year, we have detected quite a few avalanches in the last 2 years, so this helps us a lot in adjusting and optimizing our software algorithms. We also have 2 projects where we're detecting rockfall. We've detected one debris flow because they're not that frequent, luckily. There's 2 geometries that we use them, looking upwards from the valley down upwards to a mountain, or we put them, for example, on a Wiesen tower and look down. So now let's turn to Zermatt. I'd like to show you that example a bit more in detail. This is the town of Zermatt. You might know the Matterhorn here. And there are 3 avalanche paths here that threaten the road that goes to Zermatt. So it's the only road going up the valley. They have about 200 cars per day, so quite some traffic, considering it's a car-free village. We're all parked somewhere here. And they asked us if we could provide them with a radar solution that closes the road here in real time. So what did we do? We placed 2 radars on the opposite side of the valley, one monitoring this area, the yellow one, and another one monitoring this orange area. As soon as this is about 2 kilometers from here to here. As soon as we see movement here, the radar analyzes data in real time, and if it considers that's an avalanche and that the avalanche is large enough to potentially reach the road, it closes the road here with 4 barriers and 5 traffic lights. So there is 2 locations where the avalanche can overflow the road, and that's closed immediately. Now it's well possible that the avalanche stops here somewhere in between, and if we don't measure it with the lower radar within a specified time, we know that the avalanche didn't continue further down. We can then automatically reopen the road again. Currently they do it manually, but it would be no problem to do it automatically. Another reason for the lower radar is that wet snow avalanches can start somewhere here in between, and we still need to close the road for them, so they might only be detected by the lower radar. And just to show you where we detect the people, that's not far away. That's 4 radars that are back here. I'd like to take you now on a journey to Zermatt. There is a 3-minute movie that the international section of the Swiss TV did on that system that shows you nicely how it looks like and also how the local people there work with it.
The access road to Zermatt is flanked by steep mountain slopes and in the direct path of potential avalanches. When there's a high risk, explosives experts go up in helicopters and throw charges at the unstable snow layers to set off avalanches. That's routine work for Stefan on the mountain. He does this about 300 times every year.
We have a large area prone to avalanches. It has a 2.5 kilometer long potential line of breakage. In a situation like this, it's generally better to proceed with a conventional method of controlled blasts, since you can see in which direction the snow has piled up after the explosion.
To keep avalanches in check, besides these tried and true methods, Zermatt is breaking new ground in terms of monitoring and sounding the alarm. At 1,800 meters above sea level, high above the entrance to the town, an avalanche warning system has been installed. It's the first of its kind in the world and uses radar technology to monitor the start of avalanches. The system was devised by Geopraevent, a company in Zurich. Here, the system is monitoring a 2-kilometer portion of the opposite slope.
Our system uses a similar principle to the kind of radar that detects speeding cars. We send a radar wave towards the mountain, and if something starts to move, we receive a signal.
Once the signal is received, the system evaluates the data in real time. If an avalanche is detected, the road is immediately closed automatically.
With the uppermost radar, we monitor the higher portion of the mountain, up to about 2,400 meters above sea level. This system tries to detect an avalanche as soon as it begins, since we only have a very limited amount of time to close the road below.
These images from a year ago show what an avalanche would look like. This avalanche was artificially triggered. It reached the road below. Since the radar system has been put in operation, there haven't been any avalanches of this magnitude. Nevertheless, Zermatt has been able to correctly detect a few smaller ones.
Yesterday morning, for instance, there was an alarm at 8:24. We could instantly see where it was developing and observe how it broke below the Weisshorn. The avalanche wasn't in the range of the lower radar, so no emergency measures were triggered. Thanks to this information, we could correctly evaluate the risk and decide to open the road again. We were able to raise the barriers directly from our desks.
So let's turn back to the radar. We have two radars. One monitors the upper portion of the slope. The lower one is more or less looking horizontally across the valley and it monitors the lower parts. And just to visualize that again, I show you that avalanche once more from 2015. So you see how the avalanche enters here this radar band, and that's roughly the time when it's detected. Now the system needs to decide instantly if the road needs to be closed or not. With that big avalanche, of course, that's an easy decision. The road afterwards looked like that. So the radar cannot prevent, obviously, that the road is closed, but it can prevent that the car is here. So how does the system work in detail? The first step is that the avalanches need to be detected in the radar data, so there's a lot of algorithms behind that. Wet snow avalanches look different than dry snow avalanches, so we have acquired a lot of data to make sure that all kinds of avalanches are detected by the system. And it needs to decide if the avalanche is large enough to reach the road. Then the road is closed. There are fiber optical cables running from the detection system to the barriers, and as a redundancy we have a radio connection as well. And then the locals get alerted by messages, and they log in, check online where the avalanche was detected. They can check webcams as well to see if the road is covered by debris. There are 4 webcams with infrared lights for night vision along the road. So then they can open it quickly, and they do that on a smartphone or from a computer, because reopening quickly is really key here. We will close the road a few times, I'll show on the next slide, without an avalanche having hit it. And if the road is closed for too long, people will start ignoring the traffic lights, and then the system is of no use anymore. So we have here a small statistics from last winter, how many minutes it took the authorities to close the road again. First time here, that's the time between closing and opening. First time it took more than 20 minutes because they had to get used to the system, but you see how they continuously improved. So by the end of the season, the road was usually closed between 5 and 10 minutes until they reopened it again. Here is a few numbers for this first operational winter. We have detected 417 raw events. That's the events that passed our first filter stage. Then after the second filter stage, it was 27 that we identify as avalanches. There is a lot of motion here because the heliport of Zermatt is right below the radar. So we have tens of helicopters crossing our radar beam every day, and we need to make sure we don't close the road for a helicopter. Otherwise, the pilots, I guess, will start the competition that who closes the road more times. So we have 27 avalanches, and 15 of them were blasted ones. So we didn't close the road when they did blasting, because we wanted to test the system, of course, for that kind of event as well. Of those 27 avalanches, the system considered 24 as being large enough for road closure. We didn't have any huge avalanches last winter. There was slow wet snow avalanches at 20 kilometers per hour, average front speed to 80 kilometers per hour for the bit larger one. Now, none of the avalanches reached the road, so you could argue, well, that's 24 false alarms. My opinion is that if the avalanche, or if what triggered a road closure is an avalanche, and the locals would close the road as well by looking at the avalanche. And we did check every 24 of these with the locals, showed them picture, showed them where it released, and they agreed that they would have closed personally the road as well for those 24 cases. So I don't consider that false alarms. We didn't have a single road closure that was not related to an avalanche. So not by helicopters or by anything else. So in conclusions, the real-time detection of avalanches on a large area with these 90-degree horizontal opening angle radars works operationally. The radar has to decide very quickly on whether the road needs to be closed or not. When the avalanche is still high up on the mountain, on about 2,400 meters above sea level, the road is on about 1,600 meters above sea level. So there's 800 meters in altitude difference. And fast and an easy reopening is really important, because we will close the road many times more often than there actually is avalanche debris on the road. But it can be reopened automatically by this second radar. Currently, that's an issue of regulation, if that's allowed or not. So the Zermatt authorities, they would like to have the automatic reopening, but the state, the canton of Wallis, they don't allow that yet. An outlook, we are currently improving the algorithms for other mass movements, rockfall. We have 2 projects running on that, and also the brief. Thanks, and I'm looking forward to your questions.
Any questions? Not a one question. There's a question.
What kind of price tag are we looking at for that system?
Yeah, I expected that question. I have a very quick answer to that. For everything like 2 radars and all the installations, 4 barriers, 5 traffic lights, and all the diggings, it was about $500,000.
So there would be a time lag between the initiation of the avalanche, the detection of the avalanche, and the triggering of the gate system on the road. What kind of vertical feet of an avalanche path do you need in order to have that time be significant for the gate to be effective?
For this, we did avalanche simulations together with a partner. And here, the avalanche, the fastest avalanche, the big one that you saw, takes about 30 seconds from the point where we detect it to reach the road. And then obviously you have to look at how long the sections of the road are that you need to close. And here the situation is good because it's 2 very short stretches of about 50 meters each. The radar needs about 5 seconds to decide on whether the avalanche is large enough to hit the road. So we have still 25 seconds for those sections to empty.
My question is related to you said you had 417 raw events and 27 were avalanches. What were those raw events? Can you explain what the radar saw and why they were discriminated?
Yeah, these were on one hand, these were small wet snow avalanches that just stopped at them after maybe 50 meters. But it could also be in helicopters, especially if you have several helicopters flying behind each other. So kind of larger mass movements. I have an answer to Dave, who asked the question before to Walter about the SARA. So the LARA that is used here is similar technology as the SARA. It's both a frequency modulated continuous wave radar. And that's a bit different to the radars that you're using, Dave, which is just continuous wave radars. And the difference is that with our radars we can tell in which distance there is movement. So with the old radars, you couldn't tell the difference between a raindrop very close to the radar antenna and an avalanche very far away from it, or maybe a human moving very far from it. With the FMCW radars, you can tell in which distance you have what kind of movement. So that makes it much more immune against rainfall and against other things that could disturb.
I think we have time for one more.
Yes, I'm just wondering what other options you looked into, and why did you choose to go with the radar option versus, building more avalanche sheds and tunnels and other options you wanted?
Yeah, that's a question of money. Yeah. So in Switzerland, there is a very elaborated process on how to deal with those problems. So you look at the risk that somebody gets injured or killed, and you get a price on that risk, and you look at how much the risk reduction costs. And then in the end, you take the solution with the best cost-benefit ratio. So here they are discussing about galleries, but a gallery I think would cost $10–20 million, so that would be a really expensive thing. Would give you, I'd say, almost 100% risk reduction. The radar does not give you 100% risk reduction. Somebody could still ignore the traffic light and being hit by an avalanche. Or the radar could be out of order, we monitor them, but we cannot react within seconds. So right, if the sensor breaks and then 5 minutes later there's an avalanche, the risk reduction is smaller by the radar, but the price is considerably lower for them.
Thank you. I think that's a great application.